this is our very first talk. And I can tell Adam is very popular, so maybe he'll come to support me. So after this talk, you can get your Colloquium credit. So today we only have a computer because we have 3 parallel sessions running and even more than the number of tablets we have. So afterwards, you can come to this computer. The way to sign up is the same. You just input your Unix ID and then press submit. Okay? And the talk is 30 minutes. In the end, I'll take maybe a couple of questions. And then you can feel free to go to other sessions. Enjoy the event during the whole day. Don't forget that we have the free pizza in the library area after the second talk this morning. So today Adam is going to introduce or talk about a very interesting game called the 15 Puzzle. Welcome.
Thank you, Professor. I'd like to thank Professor Stoichu first, who's out of town today, but he helped me a lot throughout this process. So I'll be talking about the 15 Puzzle, which you can see here. The game is a 4x4 grid with 15 pieces labeled 1 through 15. And as I'll do now, I'll show you how to actually solve the puzzle. So I can get new configurations like this. And to solve it, I personally use the strategy of first rearranging the first row to get 1 through 4, as I'm doing now. Then to move on to the first column, which will be 1, 5, 9, and 13. Then after that, move on to 6, 7, and 8 to finish off the second row. And then finally, which is arguably the hardest part, to rearrange the 5 remaining pieces, which was easy this time, but usually you have to play around for a little bit. So that's a quick solution. Yes, there we go. All right, thank you. That's okay, so that was a quick solution just to show you that it's not that hard. Once you know how to solve it, it's pretty easy to do over and over again. I'll actually pass around a physical board just so you can play around a little, see what it's like. The game was invented in 1874 by Palmer Chapman, and really wasn't that popular at first. The way that it really gained popularity was actually in the 1880s when a man named Sam Lloyd offered $1,000 for this new challenge. What the challenge was to take a physical board like that, remove the 14, 15 pieces out of a solved board, and then switch them and resolve. So, as you can see over there, you start with configuration A, a solved board, you take 14 and 15 out to create B, and then you try to go back to A. So this challenge created a ton of popularity across America, Europe, and nobody could come up with an answer. It turns out actually that this challenge was in fact impossible and that the 14-15 challenge could not be solved. So this kind of brings up a natural question. If one configuration is impossible to solve, how many are there? What types of configurations are impossible to solve? And another interesting question, if we were to take all 15 pieces out, scramble them up and throw them back in, what's the probability that we can solve that configuration? So I want to simulate that exercise right now, so I'll need a volunteer quickly. Matt, thank you. So, Matt, can you please fill out board C 1 through 15, however you'd like, leaving the bottom right square blank to create consistency. So as I said, this exercise is essentially simulating the process of taking all 15 pieces out of a physical board and putting them back in however you'd like. Make it really tough. There we go. 15. Up top. All right. Great. So
good job.
All right. So I want to bet you $1, Matt. $1 that board is impossible to solve. You want to take it?
Let me do the math in my head first.
Quickly. We only have 30 minutes here.
Yeah, I'll bet you $1. I think it's solvable.
Okay, great. So who thinks I have a better than 50% chance of solving that? That there's a better than 50% chance that when you scramble the pieces, that it's unsolvable? Please, feel free. All right, 3, maybe 4 people. Who thinks that Matt has a better than 50% chance of winning? That there's a better than 50% chance that it's solvable? Okay, who thinks that we have equal probabilities if we were to take all the pieces out and throw them back in, that it's solvable? All right, great. Well, that final group is in fact the correct group. Of course, Professor Morgan got it. So we'll show that half of the configurations are possible to solve, and in fact that the even permutations are the ones that are possible and the odd ones are the ones that are not. So to start, we will prove this theorem, that it is impossible to move from A to B. So this is essentially the 15 puzzle. It's equivalent to move from A to B or from B to A. It's the same exercise. So first we need to build our vocabulary a little bit. So here we see a series of moves right here. This is the bottom right corner, 11, 12, 15 in the blank space. So here we see that we're switching 12, then we're switching 11, 15, and 12. So we need a way to describe these moves. So here we see on the sideboard that the definition of a cycle of length k. So for a particular set, and in our case we're looking at the 15 puzzle with 15 elements, a cycle of length k is a function or a permutation that takes the first element of the cycle, moves it to another element, which gets moved to another element, and so on. And finally, the last element of the cycle gets moved back to the first element. So we can write this cycle in this form, A1 all the way through AK, where the k terms are the terms of the cycle. So there's a special type of cycle that we'll be really focusing on at first, and that's a cycle of length 2, which can be called a transposition. So what we're going to do is we're going to set up our board. So prove we have our solved board. I won't rewrite all of the numbers, save time. But we're going to label the bottom right blank space as 16. So by doing this, we can keep track of the blank space because, after all, every single move is a transposition of one of the elements and the blank space 16. So here we see that this move is a transposition of 12 and 16. Hi. This move is a transposition of 11 and 16. Here we have 15, 16. And finally, we have 12, 16. So that's one way of describing this process. Another way of describing this process is as a cycle of length 3. So when we look at the first configuration, we have 11, which gets moved to the original 12 spot. We have 12, which gets moved to the original 15 spot, and 15, which gets moved to the original 11 spot. So this whole process can be described as the 3 cycle, 11, 12, 15. Okay, so that's what we need to know to move forward with this proof. So we have these moves. Every move can be described as a transposition of an element 1 through 15 and 16. So we have 2 ways to describe the challenge of going from A to B. So 2 ways to describe A to B. So first is the actual challenge. When we look at the board, it's simply a transposition of 14 and 15. We're just switching 2 elements. So we have 14, 15. So now, if there were a way to actually solve this challenge, to go from A to B or B to A, there would be a series of k moves that you could do, or k transpositions of an element with 16 that could bring you from one configuration to the other. So we have a k-move solution, AK16, AK minus 116, all the way down to A116. Okay, so this would be our solution. So now we need a couple theorems. So first we have that every permutation in S can be written by a product of transpositions. So here we have 2 examples. This is a product of 1 transposition, and this is a product of k transpositions. So we also have that if a permutation can be written in 2 ways, like we just did, they either both have to be made up of an even number or both of an odd number of transpositions. So this is easy. 1 transposition means that it's an odd permutation. It's made up of an odd number of transpositions. The right side will show that it's actually an even permutation, that this will always be an even number of moves. And it's really not that difficult. So when we look at A, the bottom right space is the blank space. Similarly, we have the bottom right space as the blank space in B. So that means that we have the same number of up and down moves and the same number of left and right moves, which implies that there will always be an even number of moves to go from one to the other. So we know that this is in fact even. And since we said that if we could write a permutation if we can write a permutation in two ways as a product of transpositions, they have to both be even or both be odd. We know that this is in fact not possible. So we're done with the 14-15 challenge. Not that hard to show that it's not possible. So now let's take a step back. Originally, with the bottom right space fixed as the blank space, we had 15 factorial possible configurations. We didn't know what was possible and what wasn't.
Can I just ask, just to compare what we're doing? So that
Sure.
final theorem there, are you going to prove that, or we're just believing that, or what?
No, we're just
going
proving
to
it. Yeah. No, I'm not proving it.
You're not.
Yes. So we started out with 15 factorial possible configurations. We didn't know if any were impossible. Now we're at 15 factorial minus 1, which doesn't seem like a big jump, but I'll make the argument that it is, and that in fact we just took out half of the possible configurations. The reason is that we could substitute any permutation that is odd with 14-15, and this odd equals even, or odd cannot equal even idea still holds. It doesn't, 14-15 is not special. We could have any odd permutation. So now we've made a jump to 15 factorial over 2, and that's because the number of permutations that are even will always equal the number of permutations that are odd in a given set. So 15 factorial over 2 is the maximum number of possible permutations right now. And since I said that exactly half would be possible, we're going to prove now that all of these 15 factorial over 2 even permutations are possible. So we're going to need this theorem from abstract algebra, which says that for n greater or equal to 3, an, which is the set of even permutations is generated by a product of 3 cycles (1, 2, I). So what that means is that, for I equals 3 all the way to n. So what that means is that we have these 3 cycles, a product of them, that have 2 elements fixed, and the last element can be any of the other elements in the set. So, start the proof. It'll be a proof by induction. So we need to start out with our base case, and we'll choose n equals 3. So for our base case, which will be pretty trivial, we have all of the even permutations in A3. So that consists of E, the identity, so nothing changes, the 3 cycle 1, 2, 3, and finally the 3 cycle 1, 3, 2. But we also know that E can be written as, or is equal to, 1, 2, 3 cubed, and 1, 3, 2, that 3 cycle, can be written as 1, 2, 3 squared. So that's all we have to do for the base case. We're done with that because all even permutations are now written as a product of 3 cycles 1, 2, I, where I is 3. So now, for our inductive step. So what we'll do here is that we'll assume true for n, and we'll prove true for n plus 1. Alright, so now I'll work on this over here. So we're going to have to split this up into 2 separate cases. The first case will be simpler than the second case. And the first case, so case 1, we'll have a sigma, a permutation in an plus 1. So sigma is an element of an plus 1, and the one restriction that we have on sigma is that, sigma 1 of n plus 1 equals n plus 1. So we have this permutation. It takes n elements, n plus 1 elements. It sends the first n to places we don't know, but it sends the last element, n plus 1, to itself. So we can write sigma 1 in the following way. 1, 2, 3, all the way to n plus 1, where n plus 1 gets sent to itself, and we don't know where the first n go. So when we look at this, this is simply a permutation on n elements, because n plus 1 gets sent to itself. And since we assume that it's true for n, we're done with this case. So now case 2. We'll have another sigma, sigma 2, which is also an an plus 1. And the one restriction on sigma 2 is that sigma 2 of n plus 1 equals m, which does not equal n plus 1. So we'll also write it in this way. So sigma 2 equals 1, 2, 3, all the way to n plus 1, where n plus 1 gets sent to m, and we don't know where the first n elements go. So this is truly a permutation on n plus 1 elements. So we need to create a new function, a new permutation. And we'll call that tau. So let tau equal 1, 2, n plus 1, 1, 2, m inverse sigma 2. So tau is simply sigma 2 with 2 additional 3 cycles added to it, or tacked onto it. So tau can be written in the same way. So 1, 2, 3, all the way to n plus 1. So we want to see where n plus 1 goes first. So tau of n plus 1 can be written as 1, 2, n plus 1, 1, 2, m inverse sigma 2 of n plus 1. And from here we showed that sigma 2 of n plus 1 has to go to m. So we can write this as 1, 2, n plus 1, 1, 2, m inverse m. When we look at this 3 cycle, since it's 1, 2, m inverse, m goes to 2. So this can be written as 1, 2, m plus 1, 2. And finally here in this 3 cycle we see that 2 goes to n plus 1. So we're done with that. We have tau of n plus 1 equals n plus 1. So again, we have that we don't know where the first n elements go, but n plus 1 gets sent to itself. So similar to sigma 1, we assume that this theorem is true for n. So we're done with tau because we know that the theorem holds for it. So we can also write tau as the product of 3 cycles of the form 1, 2, I. So we'll call that tau equals 1, 2, ak, 1, 2, ak minus 1, all the way down to 1, 2, a1. So now we have tau expressed as expressed in 2 different ways. We have the original definition, and we have this. So we'll set them equal to each other. Let's go through that. So we have tau equals 1, 2, ak, 1, 2, ak minus 1, all the way down to 1, 2, a1, and that equals 1, 2, m plus 1, 1, 2, m inverse sigma 2. So now our goal is to isolate sigma 2. So we'll be multiplying both sides by the same 2 3 cycles to isolate it. So those 2 3 cycles will be 1, 2, m, 1, 2, m plus 1 inverse, and then we have our original left side of the equation, so 1, 2, ak, all the way down to 1, 2, a1, and we have that equals to these 2 3 cycles again, so 1, 2, m, 1, 2, m plus 1 inverse, 1, 2, m plus 1, 1, 2, m inverse, sigma 2. So now looking at the right side of the equation, we have 1, 2, m plus 1 and its inverse, so those cancel to the identity. We have 1, 2, m and its inverse. Those also cancel to the identity. So we're left with the following. Sigma 2 equals this expression. We can also write 1, 2, m plus 1 inverse as 1, 2, m plus 1 squared. So we'll write sigma 2 equal to 1, 2, m, 1, 2, m plus 1, 1, 2, m plus 1, 1, 2, ak, all the way down to 1, 2, a1. So now we're done, because we expressed sigma 2 in our second case as a product of 3 cycles of the form 1, 2, I. So we're done with that theorem. So we have this theorem with us now, and we need to find a way to apply it to the 15 puzzle. So we know that we can write any configuration of the 15 puzzle, any even permutation, as a product of 3 cycles where 2 elements are fixed and one element can be anywhere from 3 to 15. What we're going to do is, instead of fixing 1 and 2, we're going to choose to fix 11 and 12. This doesn't actually change any use of the theorem, it's just the way that we're going to prove that we can apply this theorem to the 15 puzzle. So the main issue that we're dealing with right now is that we don't know if we can apply this theorem to a physical board. So I'll show you what I mean. So we have any even permutation sigma on the 15 puzzle. And we know that we can take any permutation and we can write it in the following way. We can write it as 11, 12, AK, 11, 12, AK minus 1, all the way to 11, 12, A1. So that's not the issue. We just proved that we could do this. The problem is that we don't know if, let's say AK is 5. We don't know if 11, 12, 5, that 3 cycle is physically possible on this board. So I'll prove that it is possible now. So the reason why I chose 11 and 12 were because we're going to essentially hide them in the corner and create these two tors so that we can move any piece into the 15 piece. And then we apply the 11, 12, 15 3 cycle, which we showed was possible here. And then we do the inverse, the opposite of what we did to move that piece into the 15 slot. So we have this original board, and we're going to take the third box over there as our bottom right corner. So here we have 11, 12, 15, and then the rest of the board is the same as the solved configuration. Okay, so this is what we're starting with. So as I said, we need these two tracks, these two tors, to move the other pieces into this 15 spot without touching 11 or 12. So what these tors will be, we'll start in the blank space. The first one will be like this, and the second one will be like this. So these are the two tors. So as you can see, we can move any piece into this spot without touching 11 or 12. Not too hard to see. So, in other words, we can find a tau k and a tau k inverse, which will be the moves moving a certain piece into this slot and then moving the piece out of that slot. And we can apply the 11, 12, 15 in between those two actions so that this expression equals 11, 12, AK. So we know this is true. We didn't know that this was necessarily possible for each other piece, but we know that these three series of moves, or 3 cycles, is possible. So we can write this sigma, or any sigma, as, so sigma equals tau k inverse, 11, 12, 15, tau k, tau k minus 1, inverse 11, 12, 15, tau k minus 1, all the way down to tau 1 inverse, 11, 12, 15, tau 1. So we're done with that. We know that every single move in this expression is possible, so we can actually generate any even permutation of the 15 puzzle, which leaves us with 15 factorial over 2 possible, and 15 factorial over 2 impossible. Where these are the evens and these are the odd permutations. Okay, so now...
Could you say again why all
Sure.
the odd ones are impossible?
Sure. Why the odd ones are impossible?
Why all the odd ones are